Ever find yourself staring at a really complex design problem and you just feel like, okay, I need to figure out the hidden logic here and fast.
Yeah, maybe you're prepping for a design review or something.
Exactly. Or you just have that itch, to really get a new concept in your field.
That drive to grasp the core idea quickly, to see past the surface details.
Yeah.
Yeah, that's where innovation often starts.
And that's pretty much what we're doing here on the deep dive. We're not about just summarizing endless reports. This is more of a targeted extraction. We take the most vital insights from the materials you, our listener, provide, and the goal to get you thoroughly up to speed efficiently.
We've really dug into your sources this time,
Mhm.
aiming to pull out those core principles and, importantly, practical applications. Give you that aha moment.
So today we are plunging into, well, it's the fascinating world of graph theory and network analysis, specifically in computational design.
Sounds complex, but it's super useful.
It is. And our source material, it's straight from the 2025 Data in Design Class '08 workshop. We'll be looking at how tools like Python and Grasshopper are used here.
Those workshops are great. They really show how computational thinking is changing design practice, bridging that gap between theory and actually making things.
Definitely. So our mission for you today, let's demystify graph analysis in a design context. We want to get past any intimidation from the code
Yeah, the code can look scary.
and really show the underlying power. And honestly, some surprising possibilities this whole approach unlocks. And helping us connect the dots is our expert.
Happy to be here. My goal is really just to provide some context, some clarity, help you see the bigger picture and how these ideas might actually apply to your design challenges.
Okay, let's unpack this then. So think about the basic pieces in your design. It could be, I don't know, a specific point in space, or maybe a room in a building layout.
The entities.
Right. Let's call each one a node. And each node, it has its own unique ID and, crucially, a location in our digital model, those XYZ coordinates.
Got it. Nodes are the things.
Exactly. Now, the connections between these things may be a path, maybe a structural beam, whatever links them, those are our edges.
And what's really cool here, I think, is how this simple idea, this abstraction, right, nodes and edges, lets us represent really complex spatial stuff or relational information in a structured way.
Yeah, it's not just a random collection of points anymore.
Exactly. You're suddenly understanding how they all connect, how they interact. It's a system.
And it's not just like a messy list of these nodes and edges either. The workshop materials, they talk about using object-oriented programming, using classes in Python like node, edge, graph. That feels like a much more organized way to handle it compared to just, say, basic lists or dictionaries. What do you think?
Oh, absolutely. Using classes is like creating a blueprint for these elements. You can define their specific properties, their behaviors. It's much more controlled, much more manageable, especially when your graphs get complicated.
Right.
The source material actually touches on this. It says something like, translated, the reason for creating a class is that you don't actually have to. Many people do everything with arrays or just dictionaries. But the reason I used a class is that it's a bit easier to abstract. So yeah, simpler ways exist, but classes help manage complexity better.
Okay, now here's where, for me, it gets really interesting. Instead of having to manually draw every single connection in our design,
Which could take forever.
right, we can tell the computer, hey, generate these links automatically based on rules we set. Like, we could literally say, connect any two design points if they're closer than 5 units apart.
And that distance-based approach is powerful. It lets you directly model proximity, spatial relationships right within the graph structure itself.
Yeah.
It really opens up possibilities for generative design where the connections kind of emerge from the rules. Instead of being explicitly drawn by hand, the source actually gives a code snippet example, doesn't it?
It does. It says, we basically create the line and then we loop through all the edge, right? But the h distance is less than 0.5. Then we want to append that edge.
Yeah, checking that distance threshold. Simple idea, powerful result.
So, okay, what does this mean practically? Like, imagine you're trying to figure out the best way for people to move through a building layout. Optimize the flow.
A common design problem.
The workshop talks about something called breadth first search, BFS. Think of it like exploring a maze, but very methodically. You check all the doors right next to you first.
The immediate neighbors.
Before you move further away, level by level, it uses a queue, apparently, to keep track of where to explore next.
Yeah, BFS is fundamental for graph traversal. It's
Yeah.
guaranteed to find the shortest path if you're just counting the number of steps or
Yeah.
connections, the hops.
And then there's this related idea, backpropagation, especially when paths have different costs. It's like, imagine leaving breadcrumbs as you explore. Once you find the exit, you look back at your breadcrumbs and retrace your steps, but you always choose the path with the fewest crumbs, the lowest cost path, to make sure you found the absolute most efficient route back.
That's a good analogy. The source material puts it very directly, something like translated. So this is just repeating. Yes,
Yes.
this is backpropagation. So after picking the smallest one, you keep finding the smallest ones.
Right. Just keep picking the cheapest next step backward.
It's iterative, exactly. Working back from the goal, always choosing the lowest cost neighbor, step by step, until you're back at the start. That's your optimal path.
Okay, but what if exploring everything is too slow? That maze could be huge.
Right, that's where smarter algorithms come in, like a search.
Ah, A. So A is like giving our search algorithm a hint, a sense of direction.
Pretty much. It doesn't just blindly explore like BFS might in some cases. It uses an educated guess, that's the heuristic function, to prioritize routes that seem more likely to lead to the goal.
So it's got intuition, sort of.
You could say that. The heuristic estimates the remaining distance or cost to the target from wherever you currently are in the graph. It really combines this estimated future cost with the actual cost you've already spent to get there.
Okay.
And by doing that, it makes much smarter choices about which path to explore next. It often finds the solution much, much faster than algorithms without that heuristic guidance, especially in big, complex graphs.
And the workshop materials, they give this really cool example of how you, the designer, can tweak this heuristic. It quotes, translated. What's interesting here is this is where you can exercise your ability, whether to add or multiply. For example, if you add but multiply by 0.1, the heuristic value is reduced.
Right.
The effect.
That's a crucial point. You can fine-tune it. By playing with that heuristic function, maybe weighting it differently, you can embed your design goals right into the search process.
How so?
Well, maybe you want to gently encourage paths that go past, say, a nice viewpoint, even if it adds a tiny bit to the distance. You can adjust the heuristic to make those paths seem slightly more attractive to the algorithm.
Huh. So you're biasing the search based on design intent.
Exactly. It's not just about the shortest path anymore, necessarily. It's about the best path, according to criteria you define.
Okay, that leads nicely into the next idea. What if some paths are just less desirable, maybe for safety reasons, or maybe they're just ugly or something?
Right. That's where weighted graphs become essential.
So weights, like adding a cost.
Exactly.
Yeah.
Imagine that shorter route goes through a dodgy alleyway. You can assign a higher weight or cost to that specific edge, that connection.
And the algorithm will see that high cost and think twice.
Precisely. It will be less likely to choose it, even if it's physically shorter, because the overall calculated path cost will be higher.
The source had a quote about this too, right? About alleys versus shopping centers.
It did. Something like, translated, here the alleyways are very bad, here there's a shopping center, so it would be attractive. But this all depends on how you write the cost function.
So it really puts the control in the designer's hands. You decide what cost means.
Totally. It could be travel time, energy use, construction cost, perceived safety, aesthetic appeal, you name it.
And it's not just one factor, is it? The workshop hints you could combine things like political value, physical cost, maybe even emotional response.
Absolutely. You can define complex cost functions that weigh and combine multiple variables. That allows for a much more nuanced, sophisticated analysis where the best path reflects a complex balance of different factors.
That's incredibly powerful stuff. Okay, moving on slightly. The workshop also briefly mentions cycle detection, finding loops in the graph.
Yeah, that's important for things like process flows. You don't want dependencies that loop back on themselves indefinitely, or maybe in a building, identifying unintended circular routes.
Makes sense. And then topological sort.
That's about ordering things based on dependencies. Imagine you have tasks, and some tasks have to be finished before others can start, like in construction.
Ah, okay, like a Gantt chart, almost.
Similar idea, yeah. Topological sort gives you a valid sequence to perform those tasks if your graph represents dependencies and doesn't have any cycles.
Gotcha. Now, we've talked a lot about the kind of nuts and bolts algorithms, nodes, edges, but there are shortcuts, right? Like libraries.
Oh, for sure. Libraries like NetworkX in Python are incredibly powerful.
Mm.
They have functions already built for tons of these analyses.
Like what?
Calculating node centrality, figuring out which nodes are most important or connected, doing that topological sorting we just mentioned, shortest path, cycle detection. Lots of stuff is ready-made.
So you don't have to code BFS from scratch every time.
No, definitely
Right.
not for standard tasks.
Yeah.
NetworkX is a huge time saver. And there are even custom Grasshopper plugins mentioned, like NNA numerical network analysis, that package these things up for visual programming.
But there's a but, isn't there? The workshop seemed to really stress understanding the basics, too.
Yes. There's a quote in the source that captures this, I think. Translated, I personally don't recommend just using libraries, but using libraries. Obvious libraries like PyTorch, TensorFlow, NumPy. Other than those, making them yourself can be even more helpful if you try it once.
So it's like, it's good to know how the engine works, even if you usually just drive the car.
Exactly that. Libraries are convenient, indispensable sometimes. But understanding the algorithms underneath gives you a deeper insight. It lets you troubleshoot better, maybe even create custom solutions when the off-the-shelf tools don't quite fit your unique problem.
Okay, let's talk about real-world impact then. How is this stuff actually used in design?
Oh, tons of ways.
Yeah.
Think about analyzing pedestrian flow in a city. Where do people walk? Where are the bottlenecks?
Uh-huh.
Or figuring out how accessible parks or subway stations are from different neighborhoods. You can use models like the Hopfield model or gravity analysis for that, which relate to network ideas.
Predicting attraction between places.
Sort of, yeah. Understanding how origins, like coffee shops, connect to destinations, like parks, based on the network structure, and maybe things like distance or appeal.
And inside buildings, too. Optimizing circulation.
Definitely. Finding the most efficient routes between rooms, analyzing how central different spaces are within the layout, using those weighted graphs to maybe guide people towards certain areas or away from others based on design goals.
The workshop had that interesting example about abandoned schools, didn't it?
It did. Analyzing them for reuse, maybe for elderly housing, thinking about walking distances, but also maybe even intentionally designing slightly longer paths if they're more scenic or encourage a bit of exercise.
Using detours for health benefits. That's thinking outside the box.
It really shows the potential to use this kind of analysis for broader social or health goals, not just pure efficiency.
So connecting this all up, graph analysis gives us this incredibly versatile framework, doesn't it, for looking at spatial relationships?
Absolutely. From the city scale right down to a single building's interior layout.
Yeah.
It helps us understand and optimize how things are connected.
All this cool analysis depends on one thing, right? Good data.
Critically important. The workshop materials really hammer this home. Clean, well-prepared data is the absolute foundation. Garbage in, garbage out, as they say.
Yeah.
And it raises that point again. The power isn't just the fancy algorithms. It's also about how well you can translate the messy real world into a clean, meaningful graph.
That abstraction step.
That abstraction step is key, getting the nodes, edges, and maybe the weights right to accurately represent your specific design problem. That's where a lot of the skill lies.
And the idea of keeping things separate, like the graph logic separate from the visualization in Grasshopper.
Yeah, separation of concerns. It's good practice. Makes your code cleaner, more robust, easier to adapt if you change the visualization part later. The core graph logic stays intact.
One last thing the workshop mentioned was probability, moving away from just saying random.
Yes. Instead of vaguely saying, I place things randomly, define clear, probabilistic rules. The quote was something like, translated, I did it randomly. Those words should absolutely never be used. How should you write it then? You should calculate it with probability.
So it's about being more rigorous, even when exploring variations.
Exactly. It shifts generative design towards something more controlled, more analyzable, less arbitrary. You define the probabilities, the conditions, and then explore the outcomes.
Okay. So let's try and wrap this up. What's the big takeaway here?
I'd say graph theory provides this incredibly powerful and really flexible way to analyze spatial and relational data in computational design. It's a core tool.
Yeah, understanding those basics, nodes, edges, the key algorithms like shortest path, BFS, backpropagation, A, that gives you a solid foundation.
And then adding weights to represent real-world constraints or preferences.
And knowing that libraries like NetworkX exist, but also appreciating why understanding the fundamentals matters.
It all combines to open up a huge range of possibilities for analysis and ultimately for optimization in design.
So for you listening, you should now have this foundational grasp of graph analysis. Enough to start thinking differently, right?
Hopefully. Enough to move beyond just intuition and start leveraging data-driven insights, using the structure of connections to inform your design process.
So here's something to mull over. Think about your own design challenges right now. What relationships are involved? Could you maybe model them as a graph?
What are the key things, nodes, and what are the crucial links edges between them?
And what questions could you start asking or even answering if you applied some network analysis? Could weighted analysis help you prioritize different design goals?
Yeah, start looking for the networks hidden within your projects. What are the unseen connections? Understanding those might give you entirely new ways to approach the problem.
And that wraps up our deep dive for today on graph theory and network analysis in computational design. It really is amazing how just understanding connections, relationships, how powerful that can be.
It changes how you see the systems you're working with, for sure, both digital and physical.